Edexcel Further Maths Core Pure 1 Specimen Paper, Question 5. Now this question involves vectors and specifically planes. So we're given this diagram and most of the blurb at the beginning is basically confirming for you what you probably suspect when you glance at the diagram. We have basic assumptions like the fact that OAFE is a rectangle, so we do have right angles. OC is vertical, so it's perpendicular to OA and OE, etc., etc. In fact, the only part of this that isn't or couldn't be part of cuboid is the sloping roof BCDG. And that is the part that the question is most interested in. Find an equation of the plane BCDG, giving your answer in the form r dot n equals d. Now the first thing we need to understand here is the format that they've given. This is the equation of a plane, but why does it work? And what is the relevance of the r, the n, and the d? Probably the best way to make sense of this is to see it in a slightly different format. R dot n equals a dot n. This is an equivalent equation, and if you think about it, if d is a scalar, it makes sense that it could come from a vector dotted with another vector. Now, the key insight will come from the next version of this thing, where we subtract a dot n from each side, and we end up with r minus a dotted with n equals 0. And this is the same equation again. But the thing about this one is, it tells us something. Whenever you have a dot product that equals 0, it tells you something about the relative directions of the two vectors. In this case, it means that r minus a is perpendicular to n. And that's the crucial element of this. Because the key thing here is that n is a vector which is normal to the plane, and a is the position vector of a point in the plane. And remember, with an equation like this, r is the variable, if you like. It's a vector variable, that's why it's in bold here, or you might write it underlined in handwritten work, but it represents a general point. So the general point represented by r is it's a point which has to be on the plane. So we're constraining it by saying that if you take the dot product of r with n, you get this particular value d that they've called it. But we can think of it more intuitively like this. It's a position of a point which, if you calculate the vector relative to a point which is on the plane, you get something which is perpendicular to n, the normal to the plane. So the crucial thing here is that if we do r minus a, we get a vector which lies on the plane. Unlike the vector a itself, which will go from the origin to a point on the plane, or the vector r, which similarly will go from an origin to a point on the plane, r minus a is the vector which goes from the point with position vector a to the point with position vector r. Therefore, it is perpendicular to n, since the whole point of n is that it's perpendicular to the plane. In other words, it's perpendicular to any and all lines which lie on the plane. If we consider this BCDG plane, the roof of this shelter, if you imagine the builder has left his spirit level or a ruler lying down on the roof, it doesn't matter which direction he lays that down, whether it's parallel with BC or parallel with DC, or perhaps it's lying at some kind of slant in between. It doesn't make any difference which direction it is. If it's lying flat on the plane, then any direction which is perpendicular to the plane must be perpendicular to that spirit level or ruler that's been left lying around. So once we understand this and we know where these numbers come from and what these vectors represent, we can construct the equation of the plane. We just need a few things. We need A, which is the position vector of a point on the plane, and we need N. A vector which is normal to the plane. How do we get them? Well, let's start with A. A can be any point on the plane. So I'm going to use the point C. The position vector of C, which we might call OC. I'm choosing that one because if we go from O, we don't have to move any distance in the I direction, we don't go any distance in the J direction, we only move 0.8 in the K direction. So it's going to be a nice simple vector to work with, 0, 0, 0.8. So that can be our position vector A. And the next thing we need to find is the normal. To find the normal, or to find a normal, I should say, because any vector which is perpendicular to the plane is a valid normal vector, we could use the cross product. I'm going to show this method even if you may not yet have come across it, because it is probably the quickest approach to doing this. The cross product of two vectors gives a normal to both vectors. So unlike the dot product, which gives a scalar result, like a dot n gives a value d, the cross product will give a vector result, and the vector that it produces, its length is important as well, but the thing we're interested in here is the fact that the vector that's produced is a normal vector to both of the original vectors you give it. So if, for instance, we did the cross product of CB and CD, we would get a vector which was perpendicular to both, and therefore it would be perpendicular to the plane. Now, conveniently enough, our calculator can deal with not just defining vectors, but cross product of vectors. So if we decide we're going to use the two vectors I mentioned, use the vector CB and the vector CD, the vector from C to B is just 3, 0, 0. The vector from C to D doesn't go any distance in the I direction. In the J direction, it moves 1.2. And in the K direction, well, it moves up from a height of 0.8 to a height of 1.5. So in total, it's moved up 0.7. So we just need to find the cross product of those two vectors. On the calculator, we can define our vectors. 3D vectors, 3, 0, 0, press enter, press option once more. We can define another vector. We'll define vector B. That's also three-dimensional, but it's 0, 1.2, 0.7. And then we go to option once more, and we can see we've got vector calc, which will allow us, if we press option, we can now select our vectors to do calculations with. Vector A cross vector B. The order in which you do a cross product does make a difference. The only difference it makes is in the sign of the answer, whether it's positive or negative values. So this one, 0 minus 2.1, 3.6, is a perfectly valid normal vector. If we'd done it the other way and got positive 2.1 and negative 3.6, that would also have been a valid normal vector. Any scalar multiple will also be a normal vector. So if it's more convenient, you can scale them. And we might do that for us. So we might say something like the n that we're going to use is going to be equal to, if we want a scaled version of that, the simplest thing to do here is perhaps to multiply all the terms by 10. So we get minus 21 and 36. And then because both of them divide by 3, we could turn that into a 7 and a 12. That might be a little simpler. Now, that's a valid normal vector and it's written in a convenient way. We can even check that it makes sense. If you try to visualize that vector, you'll find that it lies in the plane OEDC, which makes sense because it can't be pointing either even slightly in the direction of CB or in the opposite direction of CB. If CB is pointing perfectly in the I direction, then any line, any vector perpendicular to that direction must be perpendicular to the I direction. It must have no I component at all. And that's why we've got a 0 in there. In terms of the J direction, it's suggesting that it goes minus 7. In other words, it's coming away from the brick wall. And in the K direction, positive 12. So as you'd expect, it's sort of sticking up and away from the wall, but it's not moving left or right as you look at the building from the front, if your direction of view is from O to E, facing directly towards the wall. So now we've got our normal vector, and we've also got a value for A, a point on the plane. We can construct our plane equation. So we're going to use the fact that R dot n equals A dot n is a valid equation, and A dot n is something we can actually calculate. We're going to enter in our normal vector here, and for this part we're going to use 0, 0, 0.8 because that's the point on the plane. We're going to use 0, minus 7, 12. I said that it doesn't matter what normal vector you use. This is a valid normal vector. There'd be nothing wrong with using that here, but we just have to make sure whichever one we're choosing, we're using the same normal vector here and here, because otherwise you'll be scaling things differently. Remember, this comes from R minus A dot n. So to allow us to make the jump to this, and therefore to the version above, that's the one we ultimately want to end up with here, we need to make sure the n is the same for each separate part. So the right-hand side of this can, of course, be calculated. We can leave the left-hand side as is, but when we compute this dot product, we'll have 0 times 0, add 0 times minus 12, add 0.8 times 12. And 0.8 times 12 is 9.6. So that is our equation. If you've used a different normal vector, you'll get a different equation here. You might have a 2.88 or something similar if you've used just the 0, minus 2.1, 3.6. What you'll find is your version should be a scaled up or down version of mine. And in fact, you might remember that because R represents a general point in 3D, it could even be represented as x, y, z. So if they'd asked you for the Cartesian equation of the plane, you could construct it simply by doing this. And then by expanding out, so performing the dot product on the left, we'd get 0 x's, minus 7 y's, 12 z's, and a 9.6. And you can see now why if we scale down the normal vector, and we scale down at the same time the scalar on the right-hand side, then it's just equivalent to taking this equation and multiplying everything by a fixed scale factor. If we decided to call this minus 70, 120, and 96, it will be the same as multiplying everything on both sides of this equation by 10. So that's the equation of our plane. We can check by picking a point on the plane. Now you could just use a point that we know is definitely going to be on the plane because it's a corner. That would be a simple way. If we pick a point like G, for instance, it's going to have an I, J, and K component. So 3, 1.2, 1.5. 3, 1.2, 1.5 is the point, and if it belongs on the plane, when we take the dot product with 0, minus 7, 12, we're wondering if we get an answer of 9.6. And you can check this for yourself. The quickest way is the calculator. The calculator may have a dot product method here. You can see there's dot product, so we could do that. But given the simplicity of the calculation, you're probably best off just going back to normal calculator mode and doing 1.2 times -7 plus 1.5 times 12. You can always do it in your head, but it's probably quicker to make use of the calculator. So that works. And therefore we know that that particular point is definitely on the plane that we've described here. This would be the equation we'd leave. And this next bit would be only if we needed a Cartesian form. Now, that's the first part, and that was worth 5 marks. That's the majority. But the next couple of sections make use of that equation. In order to support the roof, one end of a pole is attached to the ground at the center of the rectangle and the other end to a point on the roof. This is where a good clear diagram will help you, but you want to think carefully about where that base point is for the pole. If it's in the center of the rectangle, it's going to be 3 meters in the I direction and 0.6 meters in the J direction and 0 meters in the K direction. So we have base of the pole 1.5, 0.6, 0 is the position vector of that point. I'm going to give it a label. I'll call it B. And the question is asking us about the shortest possible length, given that it's going to be going from there to some point on the roof. A shortest distance between a point and a plane is actually a problem that's been previously solved for us, and the formula book has a formula for us. And it looks something like this. So this is lifted straight from the formula book, and in its current form it looks like a bit of a mess. In reality, all that's going on is something like this. I won't go into too much detail, but A dot n hat minus B dot n hat. That's essentially what's going on. A is a point that we know is on the plane. N hat is the unit normal vector. So that's not just any old normal, but it's a normal that's been scaled down according to its size so that it has length 1. And then B dot n hat, this is the point we're interested in, and we wonder how far away from the plane that is. Essentially what this does is the following. A dot n hat tells you how far away the origin is from the plane if we're moving perpendicularly to the plane. And then B dot n hat projects the position vector from the origin to the point we're interested in and works out how far that is in that same direction, perpendicular to the plane. And by working out the distance between those two, by using this size of this minus this, that can tell us the distance from B perpendicularly to the plane. This formula, the N1 alpha, N2 beta, and N3 gamma, that's essentially the process of taking the dot product of some random point, which I've called B, with a normal vector. But then you would have to divide by the size of that normal vector to turn it into the unit normal, and that's what the square root is on the bottom. And then D here, they've got an add D, and that's because of the interesting way they've written their plane equation. It's a bit different to the way the textbook does it, and a bit different to the way I would normally do it. This D that they've got here is added on the left-hand side. Ordinarily, I would think of the value D in the same way they've used it in this exam question, where it's on the right-hand side. So the D we've used here is actually very similar, but it's the negative of theirs. Our D that we've got is equivalent to A dot N. So essentially, when they say plus D, they're subtracting A dot N. So what they really have is basically the same as this, but the other way around. And for clarity's sake, I'll put it that way around. Since we're finding the size of the difference between these two, it really doesn't matter which one we subtract from which. But again, because it's A dot N rather than A dot N hat, we have this division by the size of n. And whichever way you like to think of that, it's a relatively nice process to follow. I'm going to apply my version here directly, but you can see that as long as you've got the coordinates of the point you care about, and you've got the normal vector in whatever form you've managed to construct it, then you can use this formula directly. So we're going to say B, which is 1.5 0.60, dotted with our normal vector, and we're going to take away, now a dot n hat, we don't even need to compute. Remember, we already calculated that, that was 9.6. Up here, where we did a dot n, we've got this, 9.6. Bear in mind, we're doing a dot n right now rather than a dot n hat. So 9.6, essentially what I've got here is equivalent to having this with n instead of n hat, and then dividing by the size of n. That's what will turn it into n hats instead of n's. So once I've got all of this, I'm going to find the modulus of it to calculate the absolute value, and then I'm going to divide it by the size of n, which I can work out with a bit of Pythagoras. It's going to involve -7 squared and 12 squared, so that's something I can work out in a moment. Firstly, this dot product, 1.5 times nothing for the first item, 0.6 times -7 for the second item, and then 0 times 12 for the third item. So we'll get a minus 4.2, take away 9.6, and remember the whole thing is being modulated, and we're dividing by this awkward surd on the bottom. So we have 144 and a 49 gives us 193. And on the top we have that 9.6 and that 4.2 giving us 13.8. Remember, you've got the calculator to do the heavy lifting on these things, so if in doubt, make sure you're making use of this thing. Minus 4.2 minus 9.6 is minus 13.8. And of course, I'm just 7 squared, 12 squared is 193, so we've got our surd correct. We might want to write that in a slightly nicer way, but it's not particularly essential. 13.8 divided by root 193 can be written as a nicer surd. The calculator seems to be having some issues. If we multiply by 10, you might find it easier. Or if we write this as 138 times root 193 over 193, it probably doesn't get much simpler. So I'm going to leave it like that for now. That is the shortest distance. But in this case, all that faffing around with exact values is not strictly necessary, because it says find to the nearest millimeter the shortest length for the pole. So we need 13.8 divided by root 193. And we want an approximation. So this is exactly what we're looking for. 0.99334 something. And 3 decimal places is enough, because they've asked for the answer to the nearest millimeter, which is that. So that'll be our answer. We can check that it makes a bit of sense by looking back at the diagram and thinking about how far it would be if we went to other reasonable places on the roof. If you went straight up, for instance, from the middle straight up, you're going to end up with a height that's halfway between 0.8 and 1.5. Well, 0.8 and 1.5 have a sum of 2.3, so they have a difference of 1.15. So 1.15 meters in the middle. If you went from the middle of the base to the midpoint of BC, you would actually be forming a 0.8, 0.61 triangle. It's a scaled version of the 3-4-5 triangle. 3/5 to get to the midpoint of OA, and then 4/5 to get from there to the midpoint of BC. And the hypotenuse, the length of the pole we're talking about, would end up being 5/5, or 1 meter. So it turns out it's 1 meter if you go to the middle of BC. It's 1.15 meters if you just go straight up, and it'll be even longer if you go diagonally up to the midpoint of DG. Turns out there's a sweet spot somewhere between, which is just slightly less than a meter, 99.3 centimeters. So you'd save yourself a cool 7 millimeters, which is not a huge amount, especially when you start considering part C, the limitation of the assumption, state a limitation of the assumption that the boards can be modeled as planes. For this, you want to ask yourself, what is it that a plane is mathematically? What are we talking about when we refer to a plane? Well, a plane is flat and it is infinitely thin. So the distinction between a plane and, say, a rigid body would be that a body is three-dimensional, a plane is two-dimensional. Just like a line is one-dimensional, a point is zero-dimensional. Boards have thickness, so they cannot be precisely modeled as 2D surfaces. Also, we've got other considerations. I said that planes are perfectly flat. Boards may be warped or bumpy or have non-straight edges. I've recently built something very similar to this in the garden, and I can tell you from personal experience that building materials are not always perfectly straight. They don't always have nice, neat right angles at the edges, and your finished product will not be perfectly modeled by this vector equation, no matter how accurately you've managed to do it. So think about the kind of things that your idealized shapes have, and then think about the practical situation you're trying to model, and you should be able to come up with a few suggestions for what makes your model perhaps unrealistic when it comes to representing real life. So that was question 5.